Okay, we want to continue with polar coordinates now and look at the graphs of some equations in polar coordinates, or polar equations. I've just saved this thing over here on the board that shows the relationship between polar coordinates and rectangular coordinates. We might need that if we go to convert one equation written in polar coordinates into rectangular coordinates. But let's take a look at our first examples. R is equal to 3. That's the polar equation R equal 3. So when it says R is equal to 3, it means theta any number, or any number of degrees. So R is equal to 3. Let's start here and go 1, 2, 3 units out in this polar coordinate system. It's just going to be a circle. It's going to be all the points in polar coordinates where R is equal to 3 and theta is equal to anything. So this is the graph of the polar equation R equals 3. So R equal any number, it's going to be a circle with a radius equal to that number. So in polar coordinates, that equation, that circle right there has a nice simple equation. Remember, in rectangular coordinates, this equation is x squared plus y squared is equal to 9. So I'd have to write this, or 3 is equal to square root of x squared plus y squared. But it has a much more complicated equation in rectangular coordinates than it does in polar coordinates. So generally, things that have symmetry about the origin, that have are sort of circular in that about the origin, their equations in polar coordinates are generally simpler than their equations in rectangular coordinates. Our next one, theta is equal to 45 degrees, means theta is equal to 45 degrees, R equal any number. So we can go out as far as we want or back as far as we want on the terminal side of theta equal 45 degrees in standard position. So here is theta equal 45 degrees. We can go out as far as we want on that, or as far back as we want. So this is the line, y is equal to x here, theta equal 45 degrees. So a straight line in polar coordinates, simple equation, theta equals something, straight line that is that goes through the origin. Circle centered at the origin, nice simple equation in polar coordinates. Let's go to an equation now that has both r and theta in it. R is equal to 3 sine theta. I want to graph this equation in polar coordinates. Now, I could simply substitute in values for theta and get out values for r and collect a bunch of ordered pairs r and theta that are solutions to this equation. But I want to show you a little slightly different method of doing this, where first we graph the equation y equals 3 sine x. Just the rectangular equation y equals 3 sine x. It'll be a sine curve with an amplitude of 3. So let's see, if this is 360 degrees, 180 degrees, 90 degrees, and 270 degrees, the graph of this equation would look like this. It would go up to 3, then back down to 0, then down to negative 3, and back up to 0. So I'd get a graph that looks something like this for the graph of y equals 3 sine x. So I'm going to go over here to another coordinate system and draw in 3. And I'm going to graph r equals 3 sine theta by looking at how y changes as a function of x in this equation right here. Now theta is going to start here at 0 degrees and sweep out this curve as it goes around to 360 degrees, and r will give me the distance out on whatever ray I have. Well, that relationship is actually shown over here. As theta goes from 0 to 90 degrees, r goes from 0 up to 3. So as theta goes from 0, swings around here from 0 degrees to 90 degrees, r starts at 0 and goes up to 3. Oops, just sort of missed it right there. There's 3. Then as theta goes from 90 to 180, that is, theta swings down here from 90 to 180, r goes from 3 back down to 0. So it goes from 3 back down to 0 as theta goes from 90 to 180. Now from 180 to 270 with theta, 180 to 270, that's right in here, r goes from 0 to negative 3. So it starts at 0 at 180. By the time I get to 270 right here, I'm up to negative 3. So that swings out this part of the graph again. And then as theta goes from 270 to 360, that's here, 270 to 360, r goes from negative 3 back to 0. So negative 3 back to 0. So the graph is a circle. The graph of r equal 3 sine theta is a circle centered here at 3/2, 1.5, and with a radius of 1.5. Now let's just see for a second if that makes sense. Let's take this equation right here in polar coordinates and rewrite it in rectangular coordinates. I'll just do it real quickly. R is equal to 3 sine theta. That's R is equal to 3 times y over r. Sine of theta is y over r. Multiply both sides by r. I get r squared is equal to 3y. R squared is x squared plus y squared. Okay, let's take the 3y squared to the other side. X squared plus y squared plus 3, whoops, take that back, minus 3y is equal to 0. Now I'm going to complete the square on y. Half of this is 3/2 squared, 9/4. I'm going to add 9/4 to both sides. The left side becomes x squared plus y minus 3/2 quantity squared equals 3/2 quantity squared. Well, what is this? This is the equation of a circle with a center at 0, 3/2, and a radius of 3/2. And isn't that exactly what I have right here? The diameter, you can see, goes from 0 up to 3, so the radius is going to be right here at y equal 3/2, and the center is going to be at 0, 3/2, and the radius is going to be 3/2. So sometimes I get some justification here. If I can take a simple equation and easily convert it into rectangular coordinates, I can see that this graph does match what I'm used to getting in rectangular coordinates. This method of graphing is an alternative to making a table of ordered pairs. You can make a table of ordered pairs, but you're just going to get a series of dots, and it may take a lot of those ordered pairs and their graphs before you can actually see what the shape of this curve is. If you get used to taking your regular rectangular graphs and using them as a guide for how r and theta vary with each other, sometimes it's a lot easier then to get these graphs in polar coordinates. Plus, as you'll see after we do the next example, we also, if we have access to a graphing calculator, we can let the calculator do it for us. Let's look at our next example. Have r equals 2 plus 2 sine theta. So I'm going to do the same thing here. I'm going to graph y is equal to 2 plus 2 sine x. Okay, 2 sine x, let's see, let's put in 90, 180, 270, and 360. 2 sine x would look like this, right? So 2 sine x plus 2 is just this graph moved up 2. So where it's 0, it's going to be 2. Where it's 2, it's going to be 4. Where it's 0, it's going to be 2. Where it's negative 2, it will be 0, and then back up to 2. So this right here is the graph of y equals 2 plus 2 sine x. 2 up to 4, back down to 2, down to 0, and back up to 2. That's that graph between 0 and 360, and then it just repeats itself. Okay, let's go over here, and I'll label this 2 and 4, 2 and 4, so it sort of corresponds with this graph. Negative 2, negative 4, negative 2, negative 4. Okay, I'm going to think of theta as starting here, going from 0 to 90, 90 to 180, 180 to 270, 270 to 360. And then r is going to vary its length out on the terminal side of theta according to this graph right here. So this is r equals 2 plus 2 sine theta. As theta goes from 0 to 90 degrees, theta goes from 0 to 90, that's from here to here, r starts at 2 and goes to 4. So r starts at 2 and then goes up to 4 as theta swings out here from 0 to 90. Now from 90 to 180, r is going to go from 4 back down to 2. So it goes from 4 back down to 2. Then as theta goes from 180 to 270, that's from here down to here, r goes from 2 down to 0. So from 2 down to 0, and then from 270 to 360, here up to here, theta goes from 0 back up to 2. So I should get this sort of, I didn't draw this very well, but a graph that has this sort of nice smooth shape to it. And I found that graph by looking at my regular rectangular graph, and y varies with x here the same way r varies with theta over here, It's just that this is rectangular coordinate, this is polar coordinates, where I think of theta as sweeping out the curve as theta goes from 0 to 360. R starts at 2, goes up to 4, back down to 2, down to 0, back up to 2, and then we start the whole process over again. Next, what I want to do is take the graphing calculator and take a look at these. So let me grab my graphing calculator. Okay, so on the graphing calculator, first of all, I'm going to show you what mode I'm in right here. I've put it in degree mode, okay, and then over here I've got polar coordinates. Now let me show you my y variables. When I press y equals, I get my r's, r1 and r2, and I've got my example 3 here, 3 sine theta, and then I've got my example 4 here, 2 plus 2 sine theta. Now as far as the window goes, when we look at the window, theta minimum is going to be 0, 360 degrees, and I put it in increments of 6 degrees. Okay, theta is in increments of 6 degrees, but you can experiment with what works best. X I've got from -5 to 5, and Y I've got going from -3. Let's go down here. So you can see Y goes from -3 to 5 in increments of 1. So let me graph these. And there you can see is my first graph, which is a circle. There's a little pause while it goes around again because that circle is swept out from 0 to 180. Now here's my second graph. Okay, so you can see my second graph started at 2, went up to 4, back down to 2, then down to 0, and then back up to 2. My first graph went from 0 up to 3 and back down to 0 as theta went from 0 to 180, then it swept it out again. Now, to get a little better picture of this, I'm going to press my zoom button and go down to z square, so the calculator will square this up for me and then regraph it. Okay, there's 0 to 180, that circle is swept out. Little pause while it goes from 180 to 360. Then my second curve starts at 2, goes up to 4, back down to 2, to 0, and then from 0 back up to 2 as theta goes from 0 to 360. So you can see with the graphing calculator, I get curves that are very similar to this curve and the one I got on the previous example right here. The graphing calculator is a good way to get used to these curves, but I like my students to be able to do this relationship also, besides being able to graph these on the graphing calculator. Really shows the relationship between rectangular equations, how I can use a rectangular equation to get a graph in polar coordinates. Now I just want to explain one last thing right here on this coordinate system. I've labeled this point on the x-axis with 4, this point on the x-axis with -4. This is a rectangular coordinate system right here, and I'm just using it to sweep out my polar coordinate graph. I labeled them this way so you could see that they match the coordinates on this y-axis over here. But when I get to this point right here, this is the point 180 degrees and 2, or 2, 180 degrees in polar coordinates. In rectangular coordinates, it's still the point -2, 0. That is, the x-coordinate's -2, the y-coordinate is 0. In polar coordinates, r is 2 and theta is 180 degrees. So if you don't like these right here, we can just erase them. Okay, and we get the same exact looking graph. So anyways, that's a look at graphs in polar coordinates.